This is part one of a review of basic integration techniques. In this video, we will focus on calculating integrals based on graphs and approximating integrals using Riemann sums. For problems 1 through 3, we are given this graph of g of x, which consists of some unknown curve for x values less than 3, and then two line segments. Problem number 1. If the integral from 0 to 7 of g of x dx is equal to 3.2, what is the area of the shaded region A? Well, the integral from 0 to 7 is going to be the area between the x-axis and the curve from 0 to 7. I'm going to divide this up as three different areas. We have the shaded region A, and we also have this blue area and this yellow area. The blue area is considered negative because it is below the x-axis, while the yellow area and region A are positive areas because they are above the x-axis. If we add all three values together, we are told that it will be 3.2. That's the definite integral from 0 to 7, the net area of all three regions. The geometric area of the blue triangle is 3 over 2. That's just 1/2 base times height. So that means that the integral from 3 to 6 will be negative 1.5. Similarly, the integral from 6 to 7 is positive 0.5. The sum of all three areas is the integral from 0 to 7. So a minus 1.5 plus 0.5 should equal 3.2. Combining like terms, we have a minus 1 is equal to 3.2. And then adding 1 to both sides, we have a is equal to 4.2. And that's the answer for number 1. Number 2, what is the integral from 6 to 3 of 2 times g of x dx? First of all, when you have a constant in the front like this, you can take that constant and bring it outside the integral. So this should equal 2 times the integral from 6 to 3 of g of x dx. Secondly, notice that the limits of integration are sort of backwards. We're integrating from 6 to 3. That's from big to small. We normally integrate from least to greatest. Now we can fix this by reversing the limits of integration, but when you reverse the limits of integration, it changes the sign. So the original integral will equal negative 2 times the integral from 3 to 6 of g of x dx. The integral from 3 to 6 is negative 1.5, as we discussed earlier. So we have negative 2 times negative 1.5, which equals positive 3. So that's the answer for number 2. Number 3, find the integral from 3 to 5 of 4 plus g of x dx. When you have more than one term, you can simply integrate term by term. So the original integral would be the same as the integral from 3 to 5 of 4 plus the integral from 3 to 5 of g of x. The way to evaluate the integral of 4 is to first take the antiderivative, which would be 4x, and then apply the limits of integration from 3 to 5. So now we have this, but next we find the value at 5 minus the value at 3. So here's the value at 5 minus the value at 3. But what about the integral from 3 to 5 of g of x? The integral from 3 to 5 of g of x is represented by this blue triangle. Because it is below the x-axis, it will be a negative area. And the geometric area is 1, so therefore the integral will have a value of negative 1. So, in fact, instead of putting plus negative 1, I will just put minus 1. And this is an acceptable answer right here. Or you could just put 7. So that's the answer to number 3. For number 4 and 5, we will consider the integral from 4 to 8 of 16 over x dx. Number 4, approximate the integral using a right-sided Riemann sum, or RRAM, and 2 subintervals of equal width. First of all, the integral covers the interval from 4 to 8. So if we divide that into 2 subintervals of equal width, that would be from 4 to 6 and then from 6 to 8. When they talk about a right-sided Riemann sum, the idea is we will estimate the area under this curve from 4 to 8 using 2 rectangles. And the way we draw the rectangles, for a right-sided Riemann sum, we make sure that the right side of the rectangle touches the function like this. So let's imagine that this rectangle is going to represent the area under the curve on the interval from 4 to 6. So that means that this would be 4 and this would be 6. For the area of this rectangle, we will need the base and the height. The base of this rectangle is just the width of the interval. So, of course, from 4 to 6, that is a width of 2. Similarly, from 6 to 8, we would have a width of 2. Next, we need the height of the rectangle. Well, the height of the rectangle will be the value of the function at 6, the right side of the interval. So let me sort of highlight this. The height of the rectangle will be the value of the function at 6 for a right-sided Riemann sum, and for the interval from 6 to 8, it will be the value of the function at 8. The function that I've drawn here is the 16 over x. So the value of this function at 6 is 16 over 6, which reduces down to 8 over 3. And the value of the function at 8 would be 16 over 8, which is 2. So the area under the curve from 4 to 6 is approximately equal to the area of the first rectangle plus the area of the second rectangle. So that's going to be 2 times 8 over 3 plus 2 times 2. And we can just leave the answer just like this. If you're curious, this does equal 28 over 3. Number 5. Is the approximation described in the previous problem more or less than the true value of the integral? Give a reason for your answer. This question can be answered easily by looking at my sketch. However, first you have to understand why I drew the sketch this way in the first place. And that's because looking at 16 over x, the parent function is y equals 1 over x. And this is some of your prerequisite knowledge. You should know what this graph looks like. It looks roughly like this, where we have a branch in the first quadrant and another branch in the third quadrant, where the x and y axis are both asymptotes. The interval from 4 to 8 puts us in the first quadrant, so that's why I drew the branch just like this. Looking at the rectangle, we can see that this is going to be an underestimate because the area of the rectangle does not include this area that is under the curve. So the area of the rectangle is going to be less than the true value of the integral from 4 to 6. So we know the approximation is an underestimate, but we have to be very specific when we give a justification for this answer. I want you to memorize this chart and use it to justify whether your Riemann sum is an overestimate or an underestimate. A left or right rectangle Riemann sum will give you an overestimate or an underestimate depending on whether the function is increasing or decreasing. And you don't need to know which is which, left, right, increasing, decreasing. You can just use your sketch for that. What matters is that in this case, we are dealing with a left rectangle Riemann sum. So the justification will depend on whether the function is increasing or decreasing. Let's take a look. So we got an underestimate. We can tell that from the picture. But if our justification will be because the function 16 over x is decreasing. Putting it all together, the approximation is an underestimate because y equals 16 over x is decreasing. So to continue the side lesson, notice that the other methods, the midpoint rectangle approximation method or the trapezoidal sum approximation method, will give you an overestimate or an underestimate depending on whether the curve is concave up or concave down. For example, imagine that we did the trapezoidal sum approximation instead. So here's a trapezoid drawn. We can tell that this trapezoid is giving us an overestimate because it includes a little extra area above the curve. So the approximation is an overestimate. But in our justification, we won't say anything about the fact that it is decreasing. Our justification would be because y equals 16 over x is concave up. Actually, I shouldn't just say concave up. I should say concave up on the interval from 4 to 8. We should mention the interval in our answer to number 5 as well. For number 6 and 7, g is a continuous function with values given in the table. And g is increasing and concave up for all x. Use the information provided above to answer the questions. Number 6, which of the following would give an underestimate for the integral from 0 to 6 of g of x dx? Circle all that apply. You might circle more than one. They said g is increasing and concave up. So here is a graph that is increasing and concave up, which I will use as a model. Let's start with LRAM, that's left rectangle approximation method. So I'm going to draw a left rectangle, meaning that the rectangle will touch the function on the left side, like this. I can see that this is going to be an underestimate because this rectangle area is leaving out some of the area that is below the curve. So this is an underestimate. What about RRAM, right rectangle approximation? So let me draw a right rectangle where the right side of the rectangle touches the curve. I can see that this is an overestimate because the area of the rectangle includes some area that is above the curve. Overestimate. So I'm not going to circle that one. I'm going to skip MRAM for now, midpoint rectangle approximation. If I draw a picture of that, it's too hard to tell if we are looking at an overestimate or an underestimate. Instead, we will answer the question for trapezoidal sum approximation, TSAM, and whatever is happening for TSAM, MRAM will be the opposite. Just memorize that. So let's draw ourselves a trapezoid. So I'm going to draw a really big one to make it clear what's happening. Okay, so here's my trapezoid. You can easily see that this is an overestimate because the trapezoid area includes this extra area that is above the curve. So if TSAM is an overestimate, which we will not circle, that means that MRAM is the opposite and will be an underestimate. So we will circle MRAM. Number 7, approximate the integral from 0 to 6 of g of x dx using a trapezoidal sum and 3 subintervals indicated in the table. So the 3 intervals are from 0 to 3, 3 to 5, and 5 to 6. And that's what I've written here. So I still have my picture of a trapezoid. Notice that this is sort of a sideways trapezoid where the bases are vertical. But this vertical piece over here, this is base 1. And maybe I'll put a little B1 over here or something. So this is base 1. And this over here is base 2. The height of the trapezoid is right here. That's going to be the width of the interval. So I'm just going to go ahead and put height right here for now. What matters is that the area of a trapezoid is given by the formula 1/2 base 1 plus base 2 times the height. Let's find the area of the middle trapezoid from 3 to 5. We are going to need to know the length of base 1 and base 2. Well, base 1 is just going to be the value of the function at 3. And looking at my table, that's 6. Base 2, the height of this segment, is the value of the function at 5. So that is 8. So base 1 and base 2 are 6 and 8. Base 1 plus base 2 then is 14. Similarly, the trapezoid from 0 to 3 has base 1 and base 2 of 2 and 6. So that's going to be 8 for base 1 plus base 2. For the third trapezoid from 5 to 6, base 1 plus base 2 is 21. Back to the middle trapezoid. What is the height? Well, the height is just the width of the interval. So from 3 to 5, that's 2. Similarly, on the interval from 0 to 3, the width of the interval is 3, and that is the height of the trapezoid. From 5 to 6, the height of the trapezoid will be 1. So the integral from 0 to 6 of g of x dx will approximately equal the sum of the areas of the three trapezoids. Remember that the area of the first trapezoid will be 1/2 base 1 plus base 2 times the height. If we add an expression for the area of the middle trapezoid and the third trapezoid, we have our approximation for the integral from 0 to 6 of g of x dx. Feel free to leave your answer just like this. But if you're curious, this turns out to be 36.5.